So the question is, how would we find out or what is the logic to follow to find out the SPNE of this game? Now try to think whether P1 and P2 can be positive in equilibrium in an SPNE. So the question is, in an SPNE, can both players keep positive amounts for themselves? Okay, so suppose try to think of that question. So let me write just a minute. So the question is, can there be SPNE where P1 is positive, P1 star is an equilibrium, let's say, is positive, and P2 star is positive. So we are asking, can there be an SPNE where both players offer to keep some positive amount for themselves? Okay, so suppose there is. Okay, so suppose suppose P1 star is bigger than equal to P2 star, which is positive. Okay, so suppose that's the case, that P1 star is actually bigger than P2 and both are positive. So let's go back. Now given P1 star is bigger than equal to P2 and given 3 is a strategy or at the last node, we know that player 3 will choose player 2's, right? Player 2's offer P2, because that will give more for player 3. So in which case player 2 will get P2 and player 1 will get 0. Okay, now notice, can player 1 do better than stating a offer which is P1 star, which is bigger than equal to P2? So the answer is no. Why? Because player 1 can reduce its offer and make it something between P1 star, P2 star and 0. So it's still positive but below P2 star. In which case, so say some P1 prime, which is still positive but below P2 star. Okay, in which case 3 strategy says that 3 would actually choose this, would accept 1's offer, in which case player 1 would get P1 prime instead of getting 0, as opposed which he would have gotten had he offered P1 star bigger than equal to P2 star. Okay, but if P1 star, if player 1 wants to offer, so basically it tells you that if both payoff has to be positive, then from one's perspective the payoff, the offer P1 better be below P2 star, because only then player 1's offer will get accepted and he'll get P1 star, which is positive, rather than getting 0, in which he will get if 2's offer gets accepted. But then by the same logic, player 2 would also offer or like to offer something which is below P1, right? Because if this is the offer in equilibrium, then player 2 would be better off to undercut player 1 and choose something below P1 prime, in which case player 2's offer will get accepted and then he'll get something positive. Okay, so notice that here there is a tendency to race to the bottom, right? To always undercut the other, because if they don't undercut, then their offer gets rejected, and the player gets 0, which is worse than undercutting and getting something, a small positive value. Okay, so this undercutting incentive tells you that there cannot be an SPNE where they are both positive, where these two are positive. So it has to be the case that this undercutting will continue until they both hit 0. So basically what you get is that in equilibrium, in equilibrium, P1 star must be equal to P2 star equal to 0. Otherwise, you cannot sustain, right? So let me go back. So they'll both keep undercutting each other. So in equilibrium, it must be that they both offer 0, and then 3 is indifferent between choosing y1 and y2, because in both cases player 3 gets 100, right? And so any choice is the best response. Okay. Now this produces drastically different result than the previous case. So in the previous case, we had the similar context, but the sequence of game was different. So it was a sequential, and in each case player 3 could say yes or no to the offer. In this case, the offers are simultaneous, and player 3 looks at both the offers at the same time before saying yes to one specific person or saying no to all the offers. We see that this simultaneity introduces a competition between the two players who are offering, even though ideally there is no competition per se, right? They're both offering a particular share of the 100 rupees that they have in their pocket, but just by the sheer sequence of the game, where 3 at the end gets to see all the offers at the same time before saying yes to a specific person, introduces some competition inadvertently between the two players who are offering. Okay, and that competition leads to this kind of Batra kind of force, where they keep undercutting each other until they hit 0. Okay, so you see that by changing the sequence of the game, you can achieve drastically different result even in a very similar context, right? So that's why it's very important to be paying attention to the details of the sequence, right? So the details of the sequencing in these kinds of games, where people are offering money to the other or offering some kind of deal to the other, is very important. Okay, so I wanted to highlight that part. Now let me move on to the second example, which is sort of going to be a short example. So here is an setting. So suppose there is a classroom. Consider our classroom ACO2 LR005 or 105. In the classroom, suppose there are 3 professors who teach consecutively in the day. Okay, so then there are, say, 3 professors. Professor 1, 2 and 3 teach consecutively. In a classroom. Okay. And in each class, at the end of each class, each professor decides whether to clean the board or leave it as it is. Okay, cleaning is costly, so every time a professor cleans a board, it costs him or her -1. Okay, and if he doesn't clean, it gives him or her 0. Okay, and so it happens in sequence. So suppose professor 1 first comes in, so that's player 1, and he decides whether to clean the board or not clean the board. Okay, if professor 2 comes in, professor 2 observes whether the board is clean or not. Okay, so he knows which node he is sitting on, and if he comes to a clean board, he comes to a room where the board is clean, he doesn't have to do anything, but at the end of his class he has to clean it again. He has to decide whether to clean his stuff or not, right? So professor decides to whether clean his board and leave it unclean, and then professor number 3 comes in, who again decides the same thing, clean or unclean. Now if professor 3 comes in and finds the board unclean, then the professor has to clean the board first before he or she can take the class, after which again professor 3 decides whether he can clean the board or keep it unclean. Okay. Similarly for 2, for every node each professor has 2 options whether to clean or unclean. But if the professor enters a room which is already unclean, the professor already has to pay off -1 to conduct the class. Okay. Now if everybody cleans, so let's consider the top sequence. If everybody cleans, then everybody's payoff is -1 each, right? Because everybody cleans once. If professors 1 and 2 clean their board and professor 3 doesn't, then the payoffs are -1, -1, 0. Okay. And if if 1 cleans, 2 doesn't clean, and 3 cleans, 1 gets -1, 2 doesn't clean, 2 gets 0. 3 cleans, but 3 enters an unclean room, right? Because 2 didn't clean the room, clean the board. So in which case 3 has to clean it twice, so his payoff is -2. Okay. If they both 2 and 3 keep the board unclean, so then it's -1, 2 gets 0, 3 gets -1 because 3 already has to clean the board before conducting the class. Okay. If 1 doesn't clean and then they both clean, then 1 gets 0, 2 has to clean twice, and 3 cleans once. Here 1 doesn't clean, 2 cleans twice, 3 doesn't clean. Here 1 doesn't clean, 2 doesn't clean but has to clean at the beginning, and 3 cleans, in which case she has to clean twice. Okay. And finally if none of them clean, -1, -1. Okay, so that's the payoff. Are there information sets? Yes. Non-trivial information sets? Yes. How? If 3 enters and sees the board clean, 3 doesn't know whether 3 obviously knows that 2 has cleaned, but 3 doesn't know what professor number 1 did. Because it could be that professor number 1 also cleaned his board and 2 came and cleaned his board, and that's how the board is clean. Or it could be that 1 didn't clean and 2 had to clean the board first and then again cleaned his own writings, and then 3 walked in. So 3 doesn't know whether 3 is say here, in which case he finds the board clean, or 3 is here where he also finds the board clean. Okay, so he can't distinguish. So let me draw a line which is like this. So 3 has an information set across the first and the third node. Okay. Similarly, if 3 enters and finds the board unclean, 3 knows for sure that 2 hasn't cleaned at the end of his class. But 3 is unsure what 1 did. Okay, whether professor 1 cleaned his board or not. Okay, so again, in this node 3 finds the board unclean, and here also 3 finds the board unclean, but 3 has no clue what 1 did. So there is another information set which is across the second and the fourth node. Okay, now let's see if we can possibly apply backward induction here, even though there are non-trivial information sets. Okay, let's try to see. So let's look at the green information set. In the green information, so notice our definition of strategy. If you remember our definition of strategy, our strategy definition says that every player has to specify an action for every information set where the player makes a move. Okay, so here player 3, even though player 3 is present across 4 nodes, player 3 has to mention 2 actions for the 2 information sets that player 3 find himself in. Okay, so for the green information set, player 3 knows that if he cleans, his payoff is either -1, his payoff is either -1 or so in both nodes his payoff is -1. So if he cleans, he gets -1 for sure. Okay, because he has already entered a clean room, right? If he doesn't clean, he gets 0 no matter for the both. Oops, sorry, let me open the yeah. Yeah, sorry about that. Now in the green information set, if the player chooses, if Professor 3 chooses to clean, he incurs a cost -1. If he doesn't clean, he incurs a cost 0, no matter which node within the information set he is located in. So clearly it's best response for the third professor to not clean. Okay, on the green information set. What happens in the blue information set? In the blue information set, he finds the class to be unclean. So if he cleans, he gets -2. Sorry. Let me just write. In the blue one, he gets -2 if he cleans, and if he doesn't clean, he gets -1 here and here. So it's always better not to clean, even in the blue information set. So since he's the last mover, why would he clean, right? Cleaning is costly, and so therefore definitely optimal for him to save on that. So we see that in this specific game, even though there are information sets, we find that in each information set there is clearly an optimal action across both nodes within the information set. That need not be true generally, right? So that's why in general game we cannot apply backward induction when there are non-trivial information sets, but sometimes we can, right? So in this game, for example, even though there are information sets, we find that across the 2 nodes in each of these information set, the optimal action remains same, right? So that allows backward induction to happen. So we find that no matter what the information set is, player 3 would like to not clean. Okay, now noticing this, what is player 2's? So let's move to player 2's node here and here. In each node, player 2 has to specify an action because these are separate information sets. So on the top node, player 2, if player 2 chooses clean, player 2 knows that player 3 will choose not clean and get player 2 will get -1. If player 2 chooses not clean, then player 3 would choose not clean, in which case he'll get 0. Okay, so player 2 on the top node chooses not clean. Player 2 on the bottom node would also choose not clean, because again by not cleaning he'll get -1, and by cleaning he'll get -2. Okay, so he'll choose not clean. Now let's move to the first. Here if one chooses clean, then following the sort of arrows we find that one will get -1. Okay, and if one chooses not clean, then one would get 0, so one would choose not clean. So we see that in this game we can apply backward induction even though there are non-trivial information sets, and by applying backward induction we get this outcome where none of the professors ever clean the board after the end of the class. Okay, so that's the subgame perfect Nash equilibrium. Okay, so what is the strategy? The strategy for 1 is to choose n, for player 2 to choose n on the top node and n on the bottom node, and for player 3 is to choose n for the blue information set and n for the green information set. Okay, so this is the SPNE of the game. Okay, so let me stop here. I wanted to sort of go through these couple of examples in this class so that you get used to the various ways to think about SPNE in various kinds of games, and it will also help you do the homework assignments. So let me stop here. In the next class we will start with a new topic. Thank you.